Hi everyone, in this video we are talking about second derivatives. So we've been working all semester on first derivatives, or I guess we've been working all semester on derivatives, and the news for you today is that what we've been calling the derivative, you might also call the first derivative. And if you take the derivative of a particular function, that's what we call the second derivative. So if you were to consider the independent variable x, the dependent variable y, and let's just come up with any function f so that we let y equal that function of x. If we think of a small change, I see a typo. If you think of a very small change to the input of the function, we're going to call that delta x. So that triangle there, this is the capital Greek letter delta. And basically this delta just represents a change. So if we're talking about a small change to the input of the function, we're talking about a small change to our variable x. And if we have, a small change to the input, that's going to result in a small change to the output of the function. And we're going to call that small change in the output of the function that results from our small change in the input, we're going to call that delta y. So again, we use the capital Greek letter delta to talk about a change in the output of our function. So for every small change in the input to our function, we might have a change in the output of our function. So like this little change going from here to here, along my x-axis, we could call that delta x, because this little interval represents the change in the x value. So each end of this interval is going to map to some value in the output of the function. So this is my y-axis. Basically what we're saying is that for some change in the input of the function, that results in some change in the output of the function. So we're calling delta y and delta x those, the change in the very small change in the input and the very small change in the output that results from that change in the input. Okay. So you can think of the derivative that we've been talking about all semester as the ratio of a small change in the output of the function to the corresponding small change in the input. So we could write that ratio like this. Of course, ratio just means we're taking one thing and dividing by the other. So whenever the changes are very small, and again, reference our previous lessons, but whenever we take the derivative, we want those changes to be really, really tiny, right? In fact, the definition of the derivative says that we take the limit as that change goes to 0. So as our, that change is approaching 0, what is the difference between one output of your function minus the other output of your function divided by that change in x, right? So, you can think of h as that change in the x value here. But basically, we use this limit to say h is approaching 0 because we want these changes to be very, very small when taking the derivative. And to show that those changes are going to be really small, we wrote them as a lowercase d instead of the capital delta. And so this is just another way to write the derivative that I'm sure we're already familiar with this, right? And whenever we want to find the second derivative, so this is the new part that maybe we're unfamiliar with, we're going to write one of the following things. We have to use some kind of notation to talk about the second derivative. So we might write that we're going to take the derivative with respect to x of the ratio dy dx. Or we might say that we're going to take the derivative with respect to x of the derivative with respect to x of y, because my y is my dependent variable there. So these are meaning the same thing, hence the equal signs. But we also, for the second derivative, we might write this. We might write d squared over dx squared And basically what that's saying is, if I were to pretend I was multiplying, d times d in the numerator becomes d squared, and multiplying dx times dx, that becomes dx squared. So of course we're not multiplying those derivative operators, but the notation appears this way because I'm applying the derivative operator twice. And so likewise, you can also move the y here into the numerator, and whenever I do so, you might see something like this, d squared y over dx squared. And so I want you to be familiar with the notation we use for second derivatives. I think most of the time I'm going to use this type of notation here on the far right. But I want you to know that these are all meaning the same thing, and where that d squared y over dx squared comes from. It's talking about applying that derivative operator 2 times in a row. Now, if you have a function f of x, you can also write f double prime x. And so you write 2 apostrophes between the f and the x in your function if you're talking about the second derivative. But like I said, the way you read this out loud is f double prime x. And then maybe the last thing I'll show you, the last thing I'll say before we move on to examples, is that since whenever we said the first derivative is the instantaneous rate of change of a function, that means that taking the derivative twice, in other words, taking the second derivative represents the rate of change of what? Well, a derivative, so it's talking about the rate of change of a rate of change. And that might sound completely ridiculous, sound a little bit silly. But there's one very real thing that I think we're all familiar with, where we talk about a rate of change of a rate of change. And that is acceleration. So velocity would be the rate of change in distance over time, right? And that's a lot to write, but velocity is the rate of change in distance over time. So as time passes, what's the rate that distance is changing? That's what we call velocity. Acceleration is actually the rate of change in velocity over time. So how is your velocity changing over time, right? If you're driving in your car and you really step on the gas, the velocity of your car goes from relatively slow to relatively fast, and so you're experiencing some acceleration. Well, acceleration is a rate of change of velocity, but hey, velocity is a rate of change. And so this is what we're going to see, is that we can actually calculate acceleration as the second derivative of distance with respect to time. It's a rate of change of a rate of change. So let's do some examples. For the second derivative with respect to x of 7x to the fourth, well, let me take one derivative at a time and say that, well, my first derivative would be 7 times 4 times x to the third power, just talking about derivative power rule. So I could write that the derivative of 28x to the third. And then taking that derivative, well, 28 times 3 is going to be 84. Yeah, that should be 84. 84 and then x squared, because I bring down the 3 and multiply that 28 times 3. So it took me a minute to get 84. But this should be 84x squared, and this is the second derivative of 7x to the fourth. Okay. Now we're talking about the second derivative of e to the power 3x. And so let me first take just one of those derivatives, and I'm left with the derivative of 3e to the 3t power. And then when I take that derivative, it will become 9e to the 3t power. So this is the second derivative answer in the box. And for my last example, if I have the function f prime of x is equal to natural log x. I'm asking about f double prime of x. Well, f double prime would be the derivative of natural log x, so that would be 1 over x. So this is the first derivative already, and so if I'm asking about the second derivative, you know that the only difference between the first and the second derivative is just taking one derivative, right? Okay. Now for a car that moves according to some function describing position as a function of time, and so we're going to let position be s, and so whenever I say position is a function of time, we'll write s of t. The velocity function is the first derivative with respect to time of the position function. So like I said, the velocity is the rate of change of position over time. So also, we said this sort of before, we've sort of been alluding to this, the acceleration function, a of t, is going to be the first derivative with respect to time of the velocity function, and so that's going to mean that acceleration is the second derivative of position, or distance, with respect to time. Now, for a little application example here, suppose that we have a car during a road trip, and the position is given by this function here. This is my position function. What is the function describing the acceleration of the car during the same road trip? Well, before I jump to acceleration, I remember that, taking the derivative of position with respect to time actually gives me velocity, and then taking the derivative of velocity with respect to time, that gives me acceleration. Well, let's just take the first derivative with respect to time and figure out what that gives me for a velocity equation. So I've got 10 times natural log of t plus 1 plus 1/2 times t. When I take the first derivative with respect to time, that 10 stays the same because it's just a constant multiplier. The derivative of the natural log function should be 1 over t. And then chain rule says that I should multiply times the derivative of the inside function here. Now my inside function is going to be t plus 1. That's what goes inside my natural log function. But the derivative of t plus 1 is also just 1. And so chain rule doesn't do very much for me there. Doesn't really affect things. Now using the power rule on 1/2 t gives me plus 1/2. And this is the function that describes the velocity as a function of time. If I take now the derivative with respect to time of velocity, that's what's going to give me acceleration. So taking the derivative here, this velocity function, I could rewrite it as 10 times t to the negative 1 power plus 1/2. So the 10 stays the same, but what about t to the negative 1 power? Well, the negative 1 comes down as a constant multiplier, and then that negative 1 becomes a negative 2 with the derivative power rule. And then the plus 1/2, that's just a constant, so it goes away in the derivative. So this is actually the function that describes my acceleration as a function of time. I have one more question here. What is the value of the acceleration at t equals 10? So when we take acceleration evaluated at t equals 10, and this will be 10 times negative 1 times 10 to the negative 2 power. So that will be negative 10 divided by 10 squared, which is 100. So this is saying that my acceleration is going to be negative 1/10. So I may be decelerating at a rate of 1/10 meter per second, right? Or I could say I'm accelerating at a negative rate. But in any case, that's how you calculate an acceleration function when you're given a position function. You actually take the second derivative. So that's just one way that this idea of a second derivative is useful.